Hope your screen is visible, right? My screen is visible to you.
Yes, sir.
Okay. So we were discussing about the ideal transformer. What are the this EMF equation I have derived in a different way, as as per the Lenz law, huh? As we have seen in last class. And I'll do one thing. I'll write it on a paper and upload it. Don't follow this particular thing. How you get your EMF equation? This is not very good derivation. Okay, so in case of ideal transformer, what are the things which we assume, or which is our, I mean, the hypothetical ideal situation where fluxes produced by the primary and the secondary currents are confined within the core. So this is practically not happening whenever you have a uh, core like this, as you have seen during magnetic circuits problem. We are using a winding like this. Just a minute. স্যার আমি ক্লাস নিচ্ছি স্যার। আমি করছি। Yes, so there is a coil, and then when the alternating current or any current is produced, then there will be a flux, right? And this flux, most of the flux will be linked with the magnetic material, and other will pass through the air. So this is your leakage. Okay, so leakage flux is not there, it is assumed, but practically it is not true, as we'll see that leakage flux is there for each winding, for primary as well as secondary. And we will assume that leakage flux in terms of leakage reactance. Okay, because whenever there is a flux, then there will be inductance produced, and because of that particular inductance will have a reactance, which is omega into L, when we apply that inductance to a AC circuit. And transformer we are using with the AC supply or AC source, right? Windings have no resistance. This is also ideal situation. Windings will have resistance, but that will be very less in practical case. But you cannot totally eliminate the resistance. So resistance will be there. The core has infinite permeability. This is also not true. Core will have a BH curve, which will ensure lesser loss if you go for the cold roll grain oriented steel, or it depends on what purpose, what application you are using. If you are using for a electronic appliances, then you can use some ferromagnetic material, dust of that, or you can go even air core. So that is the special case. But for the electrical system, we have uh, CRGO steel which we use, and that will have a very thin BH loop, so that the losses are less. So infinite cannot be sorry, permeability cannot be infinite. There should be some value, and that will hold a linear relationship, and you get a saturation point like this. This is your BH curve. And negligible current is required to establish the magnetic flux. That is also not correct, because it is not infinite. So if your mu is infinite, then your reluctance is less. Then very like for minimal excitation, you will get a desired flux, but that is not the actual case, right? And lossless magnetic core, as I told, no hysteresis or eddy current loss. That is also not possible, because eddy current, although you are using laminated core, still there will be some part of it which will have eddy current loss. So those things you cannot bypass, so that we should take care, okay, when we uh, do the practical study with it. So with that ideal case, we can draw the phasor diagram with the ideal transformer. So what we are doing here, we are applying a voltage V1, which is AC, and we, with this particular voltage source, there will be current flowing through it, and that current through this coil will produce the induced EMF at this, which is trying to oppose its cause. That means polarity will be such that, or flux will be such that it is trying to neutralize the effect of V1. So this is how you get your E1. So E1 will be equal to magnitude wise V1, but sign will be negative. when there is the ideal case, when there is no leakage reactance, when there is no resistance in the primary. Okay, so then if we take V1 as our reference phasor, then E1 will be like it is shown here. E1 will be just 180 degree out of phase with it. So this is your E1 and that will be equal with V1, right? So this is what we get, and then we draw the IM, which is 90 degree lagging, because this is purely magnetic circuit. There is no resistance part, so it will have mostly, it is a inductive circuit. So if it is an ideal inductive circuit, then it will your current through it will current through this I1 will be leading by 90 degree, sorry, lagging by 90 degree. V1 will be leading I1 90 degree. So it is like this. This is your I1, which is your magnetizing component, which is your magnetizing current, which will set this flux phi. Okay, so now this flux phi will be inducing EMF E2. And once you close this when during the full I mean no load, it is open circuit, and when it is the load is connected, the flux lines will be produced in such a way that it will try to oppose the effect of this particular flux phi. Okay, so accordingly, depending on the nature of your winding, you can draw your polarity, or E1 E1 and E2 will have the same polarity, because that is how you can maintain the Lenz law here. Okay, so E1 lags Im by 90 degree, and E2 is also the same. Okay, E2 is mutually induced EMF in the secondary. So here, as we can see, this is if you look from the top, this is north pole, counterclockwise direction. So your flux line will originate from here and terminate at this. And here, when you should have your when you have to connect your load, then this is actually again in the clockwise. This is counterclockwise direction, this is in clockwise direction, right? So you should have pole. This is actually south pole, right? If the current direction like this. But if it is has to be north pole, so that it is opposing this flux, then your current should be going like this, in this direction. If the current is going like this, then we can draw the polarity like this is from positive, this is negative, this is your load when you connect your load. So that's why your E2 and E1 will be in the same phase, and just like the opposite of V1, 180 degree out of phase. Okay. So this is the ideal transformer when there is no load connected with the secondary, and in the ideal situation there is no leakage reactance, no leakage resistance, and the entire flux is linked with the magnetic material. So if these are the assumption, and if there is no core loss, and if there is no eddy current loss, hysteresis loss, then you can get a circuit like this. Now, this is the case on no load. It's a practical scenario when no load, like transformer on no load, and phasor diagram here it is given in the part B. And here we have assumed that there is hysteresis and eddy current loss. So how can you have this angle like it is shown here, this phi 0? So this is called actually hysteresis angle, and that we get from this plot. So if your BH curve looking like this, and here you are applying your current, then what will happen? Initially, when you start until you reach this zone, then there will be no flux. So it will be in the other side, right? So if you have the current waveform, if there is no hysteresis, if it is a complete linear one, there won't be any phase difference. As I told, your phi will be in phase with I. So if this is your I, then your phi will be in phase with this. But now, because of the hysteresis, you can see that the phi will look like this. This is how and there is a phase difference between these two, between your I and your phi. So if that angle between your I and phi, if that angle is something theta, then 90 degree minus theta will give you your phi 0. If theta is in phase, then theta equal to, there is no lag between I and phi, then there'll be exactly 90-degree phase shift. But in the actual case, when hysteresis is present, you get this angle, and because of that you get, if you resolve this I0, it will, you can resolve it into two term. One is magnetizing component, so this Im is your magnetizing component, which is I, it is I sine phi, and your I0 cos phi 0 is your IC, which is your core loss component, which is in phase with your V1. Can you follow this? Any doubt here? Is it okay to you how this angle we are getting? Am I connected?
Yes, sir.
Yes.
Okay, fine. So this is how we get the core loss component of I, and which is IC. So IC into V1 will give you your core loss here, because this is in phase with V1, and your IM is your magnetizing current, which will be passing through this. So this is your magnetizing current, and I0 is almost equal to IM, because core loss we try to minimize as we use lamination and we use the particular graded steel, so that we can reduce this area, we can minimize this area. So that is the aim. And then your IC will be very less. If your IC is very less, your phi 0 will be almost tending to 90 degree, almost 90 degree. So if it is closer to 90 degree, your IC will be very small and core loss component will be very small. Okay, and other thing will be as usual, because your E1 will be out of phase with V1, and that is equal and opposite, and magnitude wise same, and this is your E2. Now what is the relation between E1 and E2? E1 is the RMS value, E2 is the RMS value. So what are the relation between them? As we can see that E1 is equal to, as per Lenz's law, we can write like this: E1 is equal to minus d psi dt, right? So your, what is your psi? Psi is equal to n1 into phi, right? So we can write it is minus n1 into d phi dt, and phi remains constant. And here small e2 will be n2 minus n2 into d psi dt, as d psi dt is same. So e1 by small e2 is equal to n1 by n2, isn't it? So if the instantaneous expression has the ratio to be n1 and n2, definitely their RMS value will be also having the ratio as n1 and n2. So E1 by E2 is equal to n1 by n2, and depending on the value of n1 and n2, you get the magnitude of E2, but it will have just the 180-degree out of phase with V1. Okay, and why it is so? I told that it should have the flux line, once it is connected with load, it should have the flux line in such a way that it is trying to oppose the flux produced by the magnetizing flux produced by the primary coil. Okay, so this is how we can draw E2 to be in phase with E1. Okay, and the direction of the current will change the way we, depending on the winding, way the wear is wound over the core. According to that, your current direction will change. Okay, so now let us assume that load is earlier there was no load, it is open, but transformer on the load, assuming no voltage drop in the winding. So here it is assumed that the winding has no resistance and no leakage reactance, and then we connect our load on the secondary. Then how your diagram will change, how your phasor diagram will change, right? So as I told that whenever, as soon as we connect load, then the circuit will be closed, then there will be the current through the coil, and once there is a current through the coil, a flux line will be produced. And how the flux line will generate? It will generate such that it can oppose the cause of magnetization as per Lenz's law, right? So if we are getting a phi like this, then your current I2 will be in such a way that it will try to nullify this, counteract this phi. So if it try to eliminate this phi, then what will happen? Your net phi, if it is totally balanced, then there won't be any E1, right? And we are applying a V1 here, where V1 should be equal to E1, because V1 you have connected here, right? So if that is the case, then what will happen? There is a where, and if there is no drop across this, then it is short circuit, right? So then there won't be any transformer action. So this is not possible. So that's why what is happening when this opposite mmf, magnetomotive force, is produced by this I2 current, that will be balanced by this coil. So what it is doing, it is trying to balance this mmf. What is your mmf here? It is N2 into I2. So this mmf will be balanced by your this coil, which is having N1, and there should be a current drawn from the source, which is I1 dash, and I1 dash is equal to, or I2 dash, it is shown here. So I2 dash is equal to this. Actually, I prefer to write it as I1 dash because this is I1. So anyway, you get this I1 dash or I2 dash. Here it is written I2 dash, so I'm writing I2 dash, which is N2 I2 by N1. So your current should be drawn from the source. This current component, apart from the magnetizing component, will be drawn from the source, which will balance this MMF. Otherwise, there won't be any transformer action if it is not doing so. Okay, which is not practicable also, because whenever this is here, then there will be a magnetic component, there is a resistive drop, so there should be some voltage. It cannot be zero here when it is connected to AC. So if this is the case, then what happens? You have another component with your in the source. So from the source you are drawing I0, which is for magnetization, and that is also having two component. One is magnetizing current and another is core loss component. So that is there in I0, plus this I2 dash, which is for balancing the mmf, which is trying to reduce your magnetizing flux through the core, right? So if that is the case, then how your phasor diagram will change? This is your E1 and this is your E2. So it is drawn like same because it is taken as N1 and N2 to be same. It is drawn like this or that. So your E2 is equal to E1. But if we can increase it a bit, then this is your E2. So N2 greater than N1. This is your E2, and as there is no drop, E2 and V2 now will be in phase, because E2 is the source, then there should be some drop and then it is V2 in that way. So E2 and V2 will be in phase. Okay. And what is your current? Current is actually uh, depending on the power factor theta. Sorry, it is written as phi 2, so we should write phi 2. This is your cos phi 2 is your PF. So cos of phi 2 is equal to your PF for the load which you have connected. So this is lagging PF, as we can see from here. This is your E2. So E2 and theta 2. This is theta 2 is lagging. If it is capacitive, then it will be leading like that. We'll come to that subsequently. So this is how we are getting. And then once you have this I2, then your I2 dash will be what? I2 dash is equal to N2 I2 by N1. So what was our assumption? E2 by N2 is equal to E1 by N1. So E2 is greater than E1 means N2 is greater than N1. So if that is the case, then here also this current will be more, isn't it? Because it is N2 by N1. So we can draw the same, we can just put the 180-degree out of phase phasor, but magnitude will be N2 by N1 times more than I2. So that we have drawn, which is your I2 dash, and then there was I0 due to the magnetizing component. So this is your no load current, and this is your the component from the for balancing your MMF due to load connection in the secondary. So now you take phasor sum of these two as it is shown here. So you take the phasor sum, and this is your phi 0, which is due to the no load condition, and then once you have connected this, so this is your phi 1. Now if the phi 0 is almost equal to 90, so if there is very less core loss or hysteresis loss, then this will be closer like this, and you get almost same as this I2. So your phi 2 and phi 1, there won't be much change, right? If this angle is small, if this particular angle alpha is small, then phi 2 and phi 0 and phi 1 will be almost same phase, same angle. Okay. So this is the case when no voltage drop in the winding and equal number of primary secondary it is shown, but if it is more, then accordingly the value will change, just like that. So it is drawn with the same number of primary and secondary term. So it is the case it is shown for the transformer on no load. Already we have discussed. It should have been placed before actually this diagram. So this is your phi 0, and this is phi 2 dash, and phi 2 dash is equivalent opposite to phi 1 dash. So these are the three things. So resultant thing is phi 0 only on the no load. No load means there is no load connected. That means no I2. Oh, sorry. It is not no load. It is on load. My mistake. I'm just looking wrong thing. So when load is connected, as it is already discussed here, so then this is your phi 2. Phi 2 will be is equal to your into by I2 into I2. So that should be equal and opposite to phi 1 dash. So which is minus phi 2 dash, which is equal to N1 into I2 dash. Okay, so minus sign is because of the phasor direction of the phasor. Okay, angle phasor angle of the current. Otherwise it is same. Magnitude wise it is N1 N2 is equal to N1 I1, but phase wise it is out of phase. So here it is shown like main flux and leakage flux in transformer. So we can see there is a core. So most of the flux lines are there passing through the core itself, confined within the core, and some are through the air gap like this. So that is why, as I told, that half of the primary will be in the one limb, and half of the primary in the other limb. Similarly, half of the secondary on the one limb and half in the other limb, because if we do that, then leakage reactance will be less, losses leakage flux will be less, and that is why leakage reactance will be less. Otherwise there through air gap lot of flux will be uh, I mean leaked through. It will not connected with the, flux linkage will go, the value will go less. Okay, so these things we can represent with the help of leakage reactance, which is XL, and this is omega into L, that kind of leakage reactance. So it is inductive reactance we can call it, and there should be resistance with this coil, which is R1, and here this is R2. So those things also we should take. So X1 and R1 here, X2 and R2 there. And whenever you have load, so as per load you should have your PF for the load, whether it is inductive load or capacitive load. Based on that, your phasor diagram will also change. Okay, so here it is the example with unity power factor load, as you can see. So this is your uh, V1. So we when we draw it, for the sake of For the ease of drawing, we just take our phi to be horizontal, and this is your E1. So E1 is E1 and V1. You can write E1 is in this side, so minus E1 will be in that side, and then E1 into the drop across I1. I1, how much it is? What is your I1? I1 will be in phase with your V1. So those things you can take care, and then you can draw this minus E1 plus I1 R1 plus I1 J into X1 means it is 90 degree. So your this should be leading part, because as the current is lagging, your voltage will be leading, like in case of I mean inductive side, because in the primary side you have resistance and it's a coil, so resistance and inductance. So this is X1 is your inductive reactance, which is leakage reactance, so it will be leading like that. So I1 R1, then J into I1 X1. Then if you add this with that, then only you will get your V1. And V1 is equal to minus E1 plus I1 into J1. Okay. So this is how we can draw it. So whenever we start with, we should start like this. This is your phi as it is shown. Then this is your E1. This is your minus E1. Okay. So now it depends, whenever you are having your unity power factor load, this is your E2, this is your E2, right? And it is told that V2 is equal to this V2 plus I2 J2 is equal to E1, where Z2 is actually R2 plus J into X2. Okay. So whenever we start drawing the phasor diagram, we'll draw this, which is your E1, which is minus E1, which is minus E2. Now you have your this drop, like this I2 into R2 plus JX2 is this drop, right? And then you have your V2. So you can go like this. If this is your V1, sorry, V2, then V2 is and I2 is of same phase because it is a UPF load, right? So it will have I2 R2 and then J into like this, like the way it is shown. So then I2 into R2 plus J into I2 into X2 is equal to your E2. So this is your, this much is your I2 into R2, which is in phase with V2. Then I2 into X2 is like this. Because of R is very small, we can have like this. This is your if then your I will be more, so your drop will be less. Your drop will be same, but if your R2 is very small, then of course your I2 will be more, like the way it is shown. Then I2 into X2, and this is how you complete this side, which is secondary. So now when you have your I2, then you can get your I2 dash, which is N2 by N1 into I2. So this is your I2 dash, and that is in the 180-degree out of phase. So this is your magnetizing component, which is I0. And if you have your I2, this is your say I2 dash. Then if you complete your phasor diagram, phasor sum, it will look like this. This is your I1. So now with E1, you just in same phase, you draw I1 into R1 plus J into I1 into X1, and then you add them, these two lines, then only you will get your V1, like the way it is it is shown here. Okay. So now we should go to
Sir,
the
one
case.
thing I don't understand, sir, how V2 is actually lagging E2. What is the angle and why it is happening like this?
Why V2 is lagging E2?
Yes, sir.
Okay. So here, whenever you have this coil, this is your V2, right? This is your V2 within the terminal across load. If you measure, this is your V2. Then here, this is your E2. If there is no resistance, no reactance in this coil, then what happens? E2 is equal to V2, isn't it? Agree?
Yes, sir.
But whenever there is R, R2, which is the resistance of this coil, and the leakage reactance X2, then what will happen? Your what will be your equation? E2 minus I2 R2 plus J into X2. Sorry, I don't have annotation pen today, so my handwriting is going bad. So R2 into X2 is equal to your V2, right? So V2 plus all those things will give you your E2. So it is simple, like if you compare with your DC source, it is sourced by internal resistance, then that is your terminal voltage, like that. I mean your ideal
Yes,
case.
sir. Yes, sir.
So,
Understood.
so same way there is a drop, and as it is inductive, so your V2 will be uh, like this. There will be this lagging angle. So this is your V2, and this is your and V2 and I2 is in the same phase, so accordingly it will change. Your V2 will be lagging your E2, right? And say now we'll see how it will change when we have a capacitive load lagging, leading. So this is your difference between this is the angle which is lagging. Now uh, within V2 and this load, once you connect your load, na, V2 will remains intact, but depending on the load, what load you are using, whether you are using inductive load or capacitive load or purely resistive load, your angle between I2 and V2 will change. So accordingly, your phasor diagram will change a bit. So here what we have taken, I2 should be there in phase with V2. Okay. So that's why we get all this. So V2 plus this drop I into Z2, I2 into Z2 is the impedance, internal impedance we can call, think like that, which will be your E2. Okay, so this is how we can draw it. So once we have the entire circuit parameter, we know what is the value of the I2, what is value of the I2 will get from the load itself. If it is told that we are using this much of load, some this kilowatt load, then from there, if it is purely resistive, then we can find out what is your I square R, and from there we can get your R, and then all those things, right? Or V square by R. From there we can get R, and then we can get I2, and we can get this R2 and X2 from the characterization of the transformer. Once we can parameterize the transformer, that means when we can get the circuit equivalent, then we can get all this drop, and we can complete this phasor diagram accurately. But this is actually the rough sketch, so this is how we draw it, and that is why V2 plus this only, this is equal to your E2, right? And then if say we are using a uh, very high uh, uh, this is I mean UPF, when we use a highly inductive load with lagging PF as it is shown, this is your V2, and this phi 2 is your due to load. So this is the direction of your current, this is your I2. So once you have your V2, then from V2 then I2 into R2 drop, and then J into I2 into X2, that means I2 into Z2 will give you your E1 E2. And E2 known means, if you start with V2 actually, then you can draw like this, and then E2 known means you can get E1 when you know N2 by N1 ratio. So E1 is N1 by N2. N1 and N1 by N2 will be less than 1 here as per diagram. So you get your E1. So once you get your E1, you get your minus E1, and then this is your phi, and this is your I0. So I0, and then you can get your I2 dash in this way. You can complete your I1. So once you get minus E1, then this is drop I1 R1 plus J into I1 X1, and that if you add, then you get your V1, which is from the source. Okay. So this is how we should draw the phasor diagram. We should start actually from E1 and E2 like the way I have shown, and then start adding this V2 and then this drop, then you will get your E2. Because we don't know the exact parameter value, so we have to adjust in this way when we'll give the rough sketch of this, of the phasor diagram. So this is one case. Next is the phasor diagram with leading PF. PF means we are using a capacitive load. So if this is your V2, so if we draw our V2 like the previous way, if this is your V2, your I2 will look like this. So if this is your I2, then what will happen? Your I2, and then this is your J into, so your E2 will change accordingly. Or if it is in the other way around, so we should draw the V1 in such a way like it is shown here in the third slide. So lot of more angle between your E2 and V2, and then you can do this. So because of the parameter value is not known to us, that's why I am drawing like this. So whenever the parameters are known to us, we can draw it accordingly. Okay, so we can understand what is the angle between E2 and V2, and what is the angle between V2 and I2, all those things. So this is your V2, and then this is the phi 2, which is leading V2 because we are using a capacitive load. So then once you get this I2, you should just add I2 into R2 and J into I2 into X2. So if you join these two, then you get your E2, right? And then this is your I2. This is the direction of I2, means you have to extend this dotted line, and you have to adjust with the scaling factor n2 by n1 so that you get your I2 dash, by which your primary is drawing the current from the source and neutralizing the MMF. So this is I2 dash plus I0. Phasor sum of these two is I1. So once you get your I1, once you get your E1, you can get minus E1, then E1 into I1 into R1 plus J into I1 into X1. So if you add the phasor sum, you get your voltage V1. So this is how we can complete the phasor diagram. And from the once we have the phasor diagram, then from there we can go for the equivalent circuit. And what are the tests we carry out when we uh, try to find out the equivalent circuit for the transformer, that you have seen in your experiment on open circuit and short circuit test of transformer, isn't it? You have carried out in your ES51 laboratory. So that thing also we'll discuss, and that possibly in the next class. Before that, just let me share one problem which Harsh was asking in MS Team, sorry, not MS Team, in WhatsApp he has shared. But how can I show
Yes, sir.
the solution? Okay, let us try to show it. I have solved it. I'll share with you in WhatsApp, but still let me discuss it with a rough sketch. What was your mistake actually? So let us go to the end. Okay, so the connection was. I'll ask Harsh to open your diagram. Huh? So if you open your diagram, you can relate it because I have drawn in the same way you have drawn.
Yes, sir. Yes, sir.
Okay, so this is your A. This is your delta. My drawing is going very bad, so please ignore. This is your W1. This is your B, this is your W2, this is your C. So phasor diagram was, you have written W1 reading which is IA into VAB. Why you have taken VAB? It is actually taking VAC, na W1. It is between A and C, right? If you open your diagram, here you have written it is VAB between A and B. Angle between
Sir,
IA and VAB. Why? How it is between VAB?
no, no,
It
sir.
is
Yes,
between
VAC.
AC. So if you do that, then you should take, you have this VAB. This is BC. Sorry, this is CA. Right? So when you do this and your drawing was like this, this is your IAB, and then you should take IAC, which is in this side, and then you get the IA like this. So this is your IA. So this angle is theta plus 30. This is 30. This is theta. So between VAB and IA, it is 30 plus theta. I agree. Then if you want to take VAC, then it is nothing but minus VCA, minus VCA, right? This side. So between VAB and VCA, it is 60 degree. Between VAB and VCA, it is 120. So VAB and VAC, it will be, if you take the other side, it will be 60 degree only. And then between IA and VAB, it is 30 plus theta. So then what will be the angle between IA and AC? It is 60 degree minus 30 plus theta. So ultimately you will get 30 minus theta. Got it?
Yes, sir. Yes, sir. Actually, notation I've taken differently. So,
Uh, So I'll do one thing. I'll take photograph of the solution and then I'm sharing in WhatsApp only. I thought I'll show in class, but
okay,
I
sir.
cannot do it because the annotation pane is not working. Okay.
Yes,
So
sir.
then we conclude here today. If you have any question, you can ask. Otherwise, uh, we'll in the next class we'll continue the mm, transformer different test like equivalent circuit, and then how we can get your efficiency, then regulations, and then open circuit, short circuit test. Those things we have to discuss in the next class. Okay.
Sir, can you once again briefly explain that why the flux that is there in limb 2 need to be balanced with the limb 1? Like why N2 I2 dash should be equal to N2
Uh,
I2?
okay.
Sir,
So
just one.
what happens when what is the Lenz's law? When you try to uh, it is trying to oppose its cause, right? What is causing your EMF to be induced in the secondary? That is the flux, isn't it?
Yes,
Flux is produced by the primary coil that is linking with the secondary, and then secondary EMF will be induced. So when you connect, once EMF is induced, it is fine. That is due to your magnetizing current IM. But whenever you connect your load current load will be supplied by your E2 only, which is the induced EMF. So it will draw immediately a current, isn't it? When you connect your load with the secondary coil, then the circuit is closed. That means it will draw some current. Is it okay?
yes, sir.
So when the current is drawn, then there will be a mmf produced around the coil, because now through secondary some current is flowing, means your flux line will be produced across the secondary. So what will be the polarity of that flux line? If it is in the same direction, then what will happen? It will be violating the principle of energy. It will creating energy, right? If it, then you don't need to supply anything anyway. Your if you just give a initial thing, then it will keep on generating voltage. It will building up and up and up. So it cannot happen, na? Then what to do? Your current in the secondary will be flowing in such a way that it will try to nullify its cause. That means it generate the flux line in such a way that it is trying to oppose your magnetizing component. So if it is totally nullified, if your magnetizing current is totally nullified, then what will happen? There won't be any flux through it. Then if that happens, then your E2 E1 will also will be 0. Then V1 will be equal to E1, where E1 is equal to 0. Is it possible? It is not possible.
No, sir, transformer action will not take place.
Transformer action will not take place. Then what to do to continue this? For the working of the transformer, from the primary will draw from the source a current which will be producing a mmf which is just equal and opposite to that of the mmf produced by the secondary. Then if they balance each other, then only whatever is left, what is your magnetizing current, which is very small. So whenever there is as you have seen, when we carry out the open circuit test, then what happens? If you apply the rated voltage or near to rated voltage, then there will be a very small current will be flowing through the low voltage side, right? Isn't it?
Yes, sir.
So for the magnetization, whatever current is required, that is very very small. But whenever, as soon as you connect your secondary with a load during on load test or full load test, whatever it is, that time your current drawn will be much more compared to that of the no load test, because now apart from your magnetizing component, you should your source from source the transformer is drawing the current which will be used to balance the mmf produced by the secondary coil. Otherwise there won't be any transformer action. Okay.
Yes, sir, understood, sir.
Okay, so on Thursday, tomorrow's class, we'll discuss rest of the thing. What is your open circuit test, short circuit test, some problem based on that, and then a few problem on transformer. So in the next week, already I have posted in group your Viva for ES51. It was initially scheduled from 10 to 12:30, but because there may be the classes in the first half, so we have postpone it, and we are starting from 12 to 2:30, and then 3 to 5:30. Okay. And day before I'll send you the schedule, which roll number to group 1, which to 2. So first few roll number in first 5 roll number in group 1, the next 5 in group 2. In that way we can divide the entire students in 20 groups, and each group will be given 15 marks for the YOC examination. Okay.
Sir, also stop the recording.
Sir, can you